In this video, we're going to look specifically at fats, how they are hydrolyzed and how they work to dissolve oils and clean objects. If you find this video helpful, don't forget to share, like and subscribe, and look out for new videos. Okay, so in this video we're just going to touch on fats and hydrolysis of fats. So we've just looked at hydrolysis in the previous video, so let's look at hydrolysis of fats. So what is a fat? It's a triester. What does that mean? Well, a triester fat is this molecule here. It looks kind of complicated. So on the left here we have this these three carbons, and we have coming off these three carbons an oxygen and C double bond O, which is an ester group, and we actually have three chains coming off. Three ester groups, which is why it's called a triester. Notice we also have this alkyl chain that is usually between about 14 to 18 carbons long. Now this triester is a fat or an oil, and depending on how long the carbons are and whether there is a double bond or not will depend the type of oil that it is, from palm oil to fats that come off animals to coconut oil. They all have their distinctive number of carbons and double bonds coming off certain parts of the chain. However, if I was to take a fat and I wanted to carry out hydrolysis, so I can do hydrolysis. Often, if we want to make soap, the type of hydrolysis we do is we add sodium hydroxide dissolved in water, which is hydroxide or a basic hydrolysis. So what that will do, remember, is that splits this here into an alcohol and a carboxylate ion, and you can see the carboxylate ion will be this long chain of carbons, this double bond O, this oxygen and a minus on it. And this is what happens when we carry out this reaction. So we can boil a fat in a big, so I can take fats, so I can take oils, I can put them on top of the stove, I can put them in a big pot, and I can add some drain cleaner or some sodium hydroxide. And what it will do is it will produce this alcohol called glycerol, and it will produce three carboxylate ions or conjugate bases of the carboxylic acid. This is long chain with the O and the H attached, is called a fatty acid. Okay, and we get three of these. Now these are really quite interesting because these have very interesting properties, these carboxylate ions, and we are going to talk about how we might use these in the next slide. So how do we use these? Well, we can take this carboxylate ion and we can mix it with some sodium chloride or lots of sodium ions, and it will become a solid. This solid that it becomes is now called a soap. So it's the solid is white and it's waxy, and it's used for cleaning your hands. It is the soap. This is how soap is made, by taking this long fatty acid or weak base of the fatty acid and precipitating it with sodium ions. I can draw it very simply down the bottom here as a chain of, or a long crooked line here, where each point on the line represents a carbon, and then when it's we just exclude the hydrogen. So a chemist would look at this and go, at the end there are three hydrogens coming off, because they remember that the carbon must have four bonds, and these pointy bits in the middle have two other hydrogens. And then we would get to this part at the end. Any other different atoms are added that aren't carbons or hydrogens, we draw them in. So this is what it looks like. So this is our soap. This end of our carboxylate ion, or the weak base of the fatty acid, we were just going to call this the soap at the moment. This is the bit that's when we dissolve it in water that works. So this end here is actually attracted to water. It can make hydrogen bonds with water, and so it can have water surround it and join to the water or dissolve in the water. And actually the other end, made of just carbons and hydrogens, is hydrophobic. It doesn't dissolve in water, but what it does do is it dissolves in oil really well. Okay, so we're going to dissolve this in oil, this tail. So the head dissolves in water and the tail dissolves in oil. Now this is really useful when it comes to cleaning things, because these things here, we can just call them soap molecules now to make it easier, right? if we take those and we put them in water, and we have a bit of cloth at the bottom, this grey is some cloth with some oil on it, what will happen is these soap molecules, the hydrophobic part, which is attracted to the oil or petrol or anything like that that is sort of got big long alkane chains, will actually dissolve that a globlet of the oil around itself, but then its head, its hydrophilic part, okay, will actually dissolve in the water, and it will suspend or remove this oil off the material and suspend it in the water solution. And that's how we get rid of oily stains from our clothes or from our hands. If we want to get oil off our hands, we take the soap molecules, the tails of them dissolve in the oil or the fats or the greasy parts, the heads dissolve in the water and basically just washes them off our hands. That's how soap works. And that makes soap so useful when we want to get rid of viruses from on surfaces. Now, when we first had the coronavirus, lots of people used alcohol to try and kill the virus, but the most effective way to kill the virus is just using these wee soap particles, because these soap molecules, what happens is a coronavirus is actually surrounded by what's called a lipid bilayer or a fatty layer. So these soap molecules will go, and the hydrophobic parts, the bit that dissolve in grease and fat, will stick into that, and the grease and fat will stick to the edge of them, and the head of them, remember, will dissolve in the water. So what will happen is they will go into the layer or the outside surroundings of the virus and dissolve or pull away parts of the outside surrounding the lipid bilayer of the virus and pull it away and dissolve the heads into the water solution. Now, if they make a gap in this wall, what's going to happen is this RNA or the nuclear information that's used in the middle here to grow new viruses or to cause havoc actually escapes, and the whole virus falls apart and it is destroyed. So that makes this soap a super molecule. And you know, the fats that it's produced from are really useful organic molecules, and us knowing how to carry out hydrolysis can help save the world, one virus at a time. Okay, if you've got to this part of the video, you've obviously watched all the examples that I had on those 3 questions. Hopefully this has fortified your understanding of geometric isomers, and you are now well prepared to go and attack that exam. Good luck, and if you found this video useful, don't forget to like it, subscribe, and look out for new videos that I might put up by clicking that bell. See you later.